In this lecture, I'll go over the galvanic and voltaic cell, which is also going to be the spontaneous cell. And I'll talk about anything that's going to be related to that. I'll talk about the conditions that are going to be standard versus non-standard conditions. And when we look at a galvanic cell, voltaic cell, which are going to be the spontaneous batteries or the cells, you can say, they happen on its own. So in those cases, you would have a chemical energy that would be converted to electrical energy, you can say. What that means for a voltaic cell, the overall voltage that's going to be produced would be in a positive number, or another way of saying the E0 of the cell. So zero means under standard conditions, and it could very well be under non-standard conditions as well. So whether it's an E0 of the cell or E of the cell itself that's under non-standard conditions, it's going to be in a positive value. And we also know the delta G for those processes would be in a negative value overall, because remember, the delta G for a spontaneous reaction is going to be and a negative number. And again, that delta G could very well be under standard conditions or non-standard conditions. So what does standard versus non-standard conditions really mean? A lot of time when we're looking at these batteries and we're making these batteries, we will be dealing with standard conditions, and the standard conditions involves 1 molar concentration, 298 Kelvin as the temperature. And the other thing, I'm just going to move this a little bit to the left here. And then if there is any sort of gas involved, and sometimes you have like hydrogen gas kind of being involved in there as one of the electrodes, then it would be in a 1 atmosphere. And those would be your standard conditions. Primarily, the concentration is very important here, being 1 molar. But if the concentration is not 1 molar for those electrodes or the half cells solutions that you're going to have in there, then you're not going to be under standard conditions. And in that case, you would be under non-standard conditions. And to figure out the E of the cell or the potential that the battery is going to produce under non-standard conditions, you will be using one formula, and I'll talk about that later. And that applies to the delta G standard and the delta G non-standard as well. Now, once you have the E0 of the cell calculated, I can easily calculate the delta G standard by using this formula, which is going to be negative NF E0 of the cell. This is an important formula to kind of keep in mind. And then if I want to do under non-standard conditions, then I would certainly use the E0 of the cell under non-standard conditions. Okay. And what these terms really mean, and I'll come back to this formula again. I'll use that at some point again. But what that really means is the N is how many electrons are being transferred from like in a one side to another side, or another way of saying electrons transferred from anode to cathode. And the F is going to be the Faraday's constant, and we'll talk about that as well. And the E0 of the cell is something that you're actually going to be calculating from the standard reduction potential values. So we'll talk about that as well. A lot of information here, but just as an overall picture, make sure you know what a galvanic and voltaic cells really are. So most importantly, they are spontaneous cells where you have the chemical energy actually converted to the electrical energy, which means in this case voltage, like the batteries that we use and the remote, TV remote, the cell phones, they're all going to be the galvanic or voltaic cells, because what we're doing, we have the electrons kind of transferring from one electrode to another electrode, and you are producing the voltage whenever you have the electrons transfers from one to another. Now, once the battery is dead, you usually throw it away. But in case of, let's say, cell phones or rechargeable batteries, you actually use external source of energy to reverse the process of those electrons. Now, the process will not be reversed on its own. You have to use an external source of energy. And at that point, it's not going to be galvanic cell anymore, but rather it's going to be an electrolytic cell, also called a non-spontaneous cell, because in that case, you're using an external source of energy to reverse the flow of electrons. Now, for right now, I'm going to focus on the galvanic cell, and whatever you learn in case of galvanic cell for the electrolytic cell is kind of an opposite. Now, if I want to go ahead and create a galvanic cell, I have to have two electrodes, just like it typically you see in a battery, you would have in a positive terminal, negative terminal, and whatnot. And that's what we're going to be looking at here. So we have two half cells, and the question would be, which half cell is going to be undergoing oxidation or is going to be anode, and what half cell is going to be undergoing reduction? And to answer that question, you have to actually look at what particular set of electrodes you're using. So you have a really long list of metals and even sometimes non-metals that you can potentially use as your electrodes. And you got to look at their standard reduction potential values. That is a very standard way of writing it. It's you don't have to have only standard reduction potential values. You can also have an oxidation potential values, but most of the books only kind of focus on the reduction potential values, and that's how we want to look at it. Now, suppose for our sake, for to create an voltaic cell and to kind of explain what really happens in there, I want to go ahead and use these two electrodes. So one of the electrode is going to be made of copper, and the other electrode is going to be made of aluminum. Now, the first question I want to ask myself, which one will be undergoing oxidation and which one will be undergoing reduction? Now, to answer that question, you will be given standard reduction potential values. Now, this does not say that it's in a standard reduction potential value, but when you look at this particular equation here, you can clearly see I have copper 2 plus here, gaining in two electrons and making copper solid. All right, so since you're making copper solid here, you're gaining an electron. That means this is an electrode. This is going to be in a reduction of this electron here. And then I can also look at this aluminum. Aluminum is also gaining three electrons to make aluminum solid. So this also written in the form of reduction. So these values that you have written here, E0, that's under standard conditions, which means we're going to have the concentration of 1 molar, temperature 298, and if there isn't a gas involved, that's going to have 1 atmosphere pressure. This standard reduction potential value for copper is 0.34 and for aluminum is negative 1.66 volts. And now, once I know these standard reduction potential values, based on this, I can figure out which one I want to put it on the oxidation and which one I want to put it on reduction so that I can create a voltaic cell or a spontaneous cell. Now, whoever actually has a higher reduction potential value would like to undergo reduction. And whoever has a lower reduction potential value would like to undergo oxidation. That's how you want to memorize it. And this is going to be true whenever you're trying to create a galvanic cell, or you can say spontaneous cell. Now, in this particular case, I can see copper having in a 0.34 volts of standard reduction potential value, whereas the aluminum have a negative 1.66 volts value for the standard reduction. So that means I'm going to be having copper undergoing reduction, and I want to actually have aluminum actually undergoing oxidation, just based on those numbers. So again, remember, whoever has higher standard reduction potential value, you want to make sure that undergoes a reduction. And whoever has lower standard reduction potential value, you want to make sure that goes oxidation whenever you're trying to create a spontaneous battery, which is going to be either a galvanic cell or an voltaic cell. All right, now I know I want to have the aluminum kind of on the oxidation. So go ahead, have the aluminum electrode inserted here. So on the left side, I'm going to say this is going to be your aluminum electrode, so aluminum solid. And on the right side, I'm going to have copper electrode. That's going to be copper solid. Now I'm trying to make the oxidation on the left side and the reduction on the right side, but there is no, it's not a standard. You can have the other way around. So I could make the oxidation on the right side and it could make the reduction on the left side. You just have to know that which side is losing electron, which side is gaining electron. That's the most important thing. Now, in addition to that, I also want to go ahead and dip these electrodes in their respective solutions. So if, since I'm using aluminum electrode, I want to possibly have aluminum nitrate here, maybe aluminum sulfate here. So let's just say I want to go ahead and have an aluminum sulfate here. So that's going to be Al2, SO4, 3. That's going to be the aqueous solution. Remember, this most of the sulfates actually dissolves in water except you got the barium and some of these heavy metals like lead, mercury, and all that. But this will dissolve in water. And kind of same story on the right side. I want to have this electrode, which is a copper electrode, dipped into an aqueous solution of copper ion. So that's going to be copper sulfate aqueous. You don't have to have only the sulfate solutions. You can have any other solution that actually dissolve, or that's going to be an aqueous. It could use nitrate as well, or I could use something else that actually dissolves in water. Okay, so then in addition to that, I want to go ahead and hook those up. I want to go ahead and connect these electrodes with one another, and this is where you actually going to be producing the voltage here. All right, so I can possibly say there is like a light bulb here that you're trying to kind of brighten up. And what's going to happen on the left side, since I got an aluminum electrode and we said aluminum wants to undergo oxidation, so I want to go ahead and write it like that. So aluminum solid is going to go ahead and get converted into aluminum 3 plus aqueous and 3 electrons here. And then on the right side, I'm going to have copper 2 plus aqueous plus 2 electrons, and that is going to go on to make copper solid. Well, where they're going to come from, that we'll talk about that later. Now, why we write it like that? So we decided based on these electrode potential values that copper should undergo reduction. So we want to leave this reaction as it is. That's why we left that reaction as it is. And we want to go ahead and write the aluminum in the form of oxidation. That's why we got to flip it. So we flip the aluminum reaction because this was written in the form of reduction. So right here, we flipped it saying that we okay going to be losing 3 electrons here. So eventually what happens that we're going to be adding both of these reactions. So I want to go ahead and let's say copy this down here. And I'm going to go ahead and copy this down here. Going to be adding up these two reactions in order to go ahead and get the overall reaction of this whole battery. Now, one of the things that you have to make sure that their electrons are the same. Now, before I go there, I want to go ahead and write down their E zeros. So the standard electrode potential value for the copper is going to be 0.34 volts that we got up here is coming from that number right there. And the standard reduction potential value for the aluminum was actually negative 1.66. This is where you got to be a little bit careful with. Aluminum, we are actually undergoing oxidation, not reduction. So what that really means, or how I want to relate this reaction with this reaction I have written up here, is just in the reverse of that. So this was written in the form of reduction. Now, this is written in the form of oxidation, so that means the E0 for this particular one is just going to be an opposite in sign. So this would be 1.66 volts in that particular case. So when I go ahead and add them up, I can just go ahead and add up the E zeros of each of those individual electrodes to find the E0 of the overall battery or overall the cell here. Now, before I do that, I got to make sure the electrons that you got here, they're the same. So however many electrons the oxidation is losing, that's how many reduction should be gaining at the same time. So you can kind of see here the electrons that aluminum is losing 3 here and the copper gaining 2, they're not really the same. So to kind of get those to be the same, I can go ahead and multiply the top one by 2 and bottom one by 3. So when I go ahead and do that, I'm just going to go ahead and I'm just going to copy this down here. So when I multiply that by 2 and 3, I'm going to get, let's say, 2 here, 2 here, get 6 electrons here. And then I'm also going to get 3 here, 6 electrons here, and 3 here. Now, whenever you are multiplying to kind of get the number of electrons kind of balanced out on both half cells, you will multiply these coefficients here, but then remember, you don't do anything to the standard reduction potential values at all. So even though you have multiplied these reactions, the top one by 2 and the bottom one by 3, you do not multiply the E zeros of those individual electrodes by those numbers. So those stays as it is. So I want to go ahead and add them up. The electrons kind of cancels out because they're going to be on both sides. And I end up getting 2 aluminum solid plus 3 copper 2 plus aqueous. And that is going to go ahead and make 2 aluminum 3 plus aqueous and 3 copper solid in there. That's going to be your overall balanced equation. And your E0 for this overall cell, when I add up 1.66 and 0.34, is going to be 2.00 volts. So this is how you find the standard cell potential by adding the electrodes of the oxidation half cell and the reduction half cell. And this right here, we were talking about that earlier. So the E0 for this one is, for this particular setup of the battery, is actually going to be 2.00. Now, it does come out to be in a positive value, which means it's in a spontaneous battery here. Now, if I want to go ahead and calculate the delta G standard, I will do N negative NF and then E0 of the cell. Now, N is the number of electrons being transferred. So how many electrons are being transferred here at a given time? It's not going to be 2 or it's not going to be 3. That's why we actually balanced it. So the number of electrons are being transferred here during this whole balanced equation is actually going to be 6. So that's something you got to keep in mind. Sometimes you may have the same electrons, the oxidation losing, the same number of electrons, the reduction gaining. In that case, you don't have to worry about balancing those too much. But here, I got to make sure I balance those. So this is going to be 6 moles of electrons being transferred. F is going to be the Faraday's constant, which is going to be 96,500. The exactly, I think, is like 96,400 something, but let's just say it's going to be 96,500 coulombs per mole of electrons. That's going to be the units for the Faraday's constant. And your E0 of the cell comes out to be 2.00 volts. Now I can do all this math here. Okay, I got this number right there. This coulombs times the voltage is actually going to be joules because that's how we measure the delta G in anyway. So I can go ahead and write this down as 1158 kilojoules. Let's say I want to go ahead and get rid of those 3 zeros at the end and write them in kilojoules form. And that's how much delta G you're going to be getting out of this particular battery in this particular case. And now let's go back and look at some of the very specific things that's going to be happening as soon as the battery starts working. So I know what's undergoing oxidation. So this would be your oxidation half cell. This is a reduction half cell. All right, oxidation half cell, or this electrode right here, is going to be called an anode. The electrode on the right side is going to be the cathode, or the reduction one is going to be the cathode. This anode is going to be the negative terminal of the battery, and the cathode is going to be the positive terminal of the battery. So make sure you know your terminals, make sure you know your anodes, cathodes, and all that. Now, how does this really work? So focus on the electrodes here. So I got this aluminum electrode here. And the aluminum electrode is going to lose the electrons. So here it's losing 3 electrons, but in a balanced equation, it would be 6 altogether. When it loses those electrons, this makes an aluminum 3 plus. So what's going to happen, this aluminum 3 plus is going to come off from this electrode because this electrode is made of aluminum. It's going to lose electrons, and those electrons will be traveled through here. So it's traveled through here and it's spontaneously traveling. You're not doing anything. This aluminum is willing to lose electrons and the copper is willing to gain those electrons. And as a result, there is a circulation of the electrons. And anytime you actually um, move the electrons, there is going to be a production in the voltage. So whenever you are moving the electrons, the voltage is going to be produced here. And when the voltage is produced, I can use that voltage to light up a light bulb, or I can just use it to do whatever I want, like, like charging cell phones and all that. Not necessarily charging. Charging in a cell phone is an electrolytic cell, but using the cell phone. Whenever you're using the cell phone, you are doing or watching something or using the apps and all that. So it's actually using the energy, and that energy is actually coming from the chemical energy that's going to be stored in there, because that's chemical energy is converted into electrical energy in that case. So all those electrons going to come down here, and once the electrons kind of reaches on this reduction half side, those copper 2 plus will be gaining those electrons. So I'll come back to that in a minute, but let's go back to this aluminum electrode. So as soon as this loses the electron, where the aluminum 3 plus go, because that was the side product that was actually being made here. So that aluminum 3 plus actually gets off and it goes into the solution. So what's going to happen eventually over time? Remember, this is in a solution of an aluminum sulfate, which is in a neutral solution because you have the charges of plus and minuses balanced by aluminum 3 plus and the sulfate 2 minus here. But now you start putting more aluminum 3 plus. So as a result, what's going to happen? You're going to start building up in a positive charge in the solution. All right. So keep in mind, as soon as the cell starts working, the positive charge starts to build up here. So positive charge start to build up. This is very important. Okay, now let's see what's happening in the right side. So on the cathode here, we get in a copper 2 plus. Where that copper 2 plus is coming from? Remember, I got this copper sulfate solution that this electrode is dipped in. So the copper sulfate solution has a copper 2 plus. So that copper 2 plus is going to gain 2 electrons to make copper solid. Where does that copper solid go? That copper solid, now it's going to be neutral. It's going to start getting deposited onto the electrode here. So it gets deposited onto the electrode, and now you're gonna have just an SO4 2 minus left here. Because remember, before you have an equal amount of copper 2 plus and SO4 2 minus here, you started using copper 2 plus and start getting that copper 2 plus deposited onto the electrode, leaving a lot of sulfate behind. So as soon as the cell starts working, this starts to build a negative charge. Now that's in a problematic. Anytime you have these cells kind of building up on a positive or negative charge, it's gonna eventually stop working. And to kind of you know we solve that problem, we use something called an assault bridge. So the question will come in like, why are you really using the salt bridge? And ideally, the salt bridge is typically used to kind of make sure that we're not building any excess charges on any of those half cells. So since a typical salt bridge would have something like, let's say, KNO3. So this KNO3, what's going to be happening in here, I would have K plus and I would have NO3, 1 minus. Now, since I have a lot of or positive charge starts to build up on this left electrode here, I would have all the nitrate or the nitrate starts pouring in to balance out that positive charge build up there. And on the right side, I had a negative charge build up. And to kind of neutralize that negative charge build up, I would have K plus starts pouring in this particular solution on the right side. So that is the purpose of salt bridge, just to kind of make sure there is no excessive buildup of the charge. Now let's go back to this electrode on the left side. We did say that aluminum electrode starts to lose electron. Those electrons traveled on to the other side, and then during the process, we have aluminum 3 plus being made. So where that aluminum 3 plus go, that's the question. The aluminum 3 plus goes into the solution, and that means I start losing the aluminum from the electrode. So this electrode on the left side, it would eventually gonna lose the mass. So some question will come up, which electrode loses the mass over time? And on the right side, the copper starts building up onto that electrode. That means the electrode on the cathode on the right side, it starts to gain mass. So remember that, who loses mass and who gains mass based on these reactions and why they exactly do so. Okay, now going back to these solutions that we got in there, aluminum sulfate here, copper sulfate, very likely I'm going to have a 1 molar of these solutions and 1 molar of copper sulfate. Those are your standard conditions. And anytime you go away from the standard conditions, that's when you're not really in the standard conditions anymore. And I want to go ahead and talk about that as well. But before I talk about that, I want to go ahead and write down on a cell notation. Cell notation is kind of a quicker way of writing who is undergoing oxidation and who's undergoing reduction. So in a typical cell notation, I'll write down the oxidation half cell first. So in an oxidation half cell, I have aluminum solid converted to aluminum 3 plus, and then I have an salt bridge. So these two bars that you got here, those actually represent salt bridge. And then on the reduction side, I have copper 2 plus actually converted to copper solid. So that's how you want to write down the cell notation. This will tell you who's undergoing oxidation, who's undergoing reduction. Now, let me go back for a minute and just kind of review everything what we just did. We decided based on the standard reduction potential values who's gonna be going reduction, who's gonna be going oxidation. And typically, if I'm making in a voltaic cell or in a galvanic cell or a spontaneous cell, I want to use the electrode that has higher standard reduction potential value on the cathode or undergoing reduction. And whoever has a lower standard reduction potential value, I want to make sure that undergoes oxidation. So between these two pairs that I was using here, copper and aluminum, I saw that aluminum has a lower reduction potential value. So I want to use that on the oxidation side, and copper having higher reduction potential value, I want to use that on the reduction side. Now, how do I know these are reduction potential values? Because that's how the reactions are written. Here, you gaining electrons, and remember the reduction is indeed the gain of electrons. Sometimes if you're not given the reactions, they may just write down something like E0 of reduction. So that tells you that, okay, we are talking about reduction potential values for those electrodes. Now, after that, I go ahead and put aluminum electrode on the left side here, and write down this in the form of oxidation. Okay. And whatever is going to be the oxidation half cell in a spontaneous cell is going to be the anode, and that's going to be in a negative terminal. How do I remember this in a negative terminal? Because you got, kind of an N in the anode, and negative also has an N, so that's how I kind of memorize that. And then you go ahead and start losing the electron. When you're losing the electron, you start losing the mass of that electrode, and that cation is going to start going into the solution. Now, once that cation goes in the solution, it starts to build up the positive charge. Now, to compensate or neutralize that buildup of positive charge, you're going to have anion from the salt bridge pouring into that half cell so that there's no excessive buildup of the charge. The electron travels spontaneously on the other side, and anytime electrons travel spontaneously on the other side, there's going to be a production of voltage, which means electrical energy, and that energy you can use to kind of use up the cell phones or use of the TV remote or anything like that. And then those electrons has to go somewhere, because you got to make sure you complete the circuit. They go on the cathode here. On the cathode here, you got the copper sulfate solution that's going to be gaining in 2 electrons and eventually going to be making copper solid here. And that copper solid get deposited onto this electrode. So this electrode eventually gain mass. Now, once you have all the aluminum lost from this electrode, that means I don't have any aluminum left in there to lose electron, and that's when the battery is going to be dead, or you just kind of throw it away at that point. But now suppose if you had this battery, like in a rechargeable battery. So in that case, what do? You want to reverse the process. And in terms of reversing the process, you actually want to go ahead, make sure the electron actually travels back. And that's not going to happen on its own because that's not what they're willing to do. They willing to do like where the aluminum is losing electrons and copper 2 plus is gaining electrons. When I'm trying to reverse the process, I would be having this copper solid that's deposited here to have this lose electron, which it's not going to do on its own. That's why you use an external source of energy. That's when you're charging the battery or charging your cell phone and all that thing. So I'm using an external source of energy where I reverse this whole process. All right. So once this whole process kind of reversed, that would be an electrical or electrolytic cell or a non-spontaneous cell in that particular case. So once you know the idea of galvanic cell or spontaneous cell, you can kind of think a little bit opposite in terms of the motion and all that, and that would be your electrolytic cell. In terms of electrolytic cell would have a negative value for the E0 of the cell and a positive value for the delta G, because remember, it's a non-spontaneous battery. Okay. Now, the other thing I want to talk about, what if this was actually not under standard conditions? So this whole thing we calculated under standard conditions. Under non-standard conditions, I could very well have, let's say, aluminum 3 plus being, let's say, 2 molar and copper 2 plus being, I don't know, let's say 1.5 molar. How do I account for that? And this is when you use something called an inertness equation to kind of compensate for these changes in the molarities from the standard conditions. Because under standard conditions, remember, this would have been 1 molar and this would also been 1 molar. So then you don't have to worry too much about it. But under non-standard conditions, they may not be 1 molar, and sometimes you may even change the temperature. But most of the time, we just kind of play with the conditions of the concentrations. So then in that case, the E0 of the cell is going to be equal to E standard 0 of the cell, and then minus 0.0592 over N and log of the reaction quotient here. So the reaction quotient here, what that's going to be, let's go back up here and look at the overall reaction. So in the overall reaction, you're seeing the aluminum 3 plus on the product side and copper 2 plus on the reactant side. We're not going to be including any of the solids because remember, in equilibrium constant expressions, you do not include the solids and liquids. Here, I want to go ahead and include aluminum 3 plus on the product side. So the reaction quotient would have been aluminum 3 plus. And I'll also want to take care of the coefficient. So that's going to be 2 in the power. And you're going to have copper 2 plus. That's going to have 3 in the power. So those concentrations were given. And all I really got to do is just plug those in here and kind of do the math. So I have E0 of the cell, we calculated that to be 2 volts. So 2.00 volts minus 0.0592 N is going to be the moles of electrons being transferred. That would be 6. And that's going to be log. And I'm going to have aluminum 3 plus concentration, which is going to be 2 molar square. And then the copper, I don't want to write down the units, just the numbers are fine here. And a copper 2 plus concentration is 1.5 power 3. Okay, do all this math and whatever you get, I'm not going to do this math here for you, but you can just go ahead and do the math here. And whatever you get, that is going to be that's going to be the cell potential of this particular battery under non-standard conditions. And if I was doing this under, or if I want to go ahead and calculate the delta G at this point, the delta G non-standard would be negative NFE of the cell. So pretty much got everything. I got N, I know F, and the E of the cell is going to be this number that you just have calculated. So this will still come out to be a negative, and this will still come out to be a positive, as long as you mess up the concentration so much where, this terms becomes kind of bigger than this term, then this may come out to be in a negative number. And in that case, this battery becomes non-spontaneous. So that's something you don't want to do, um, typically. So this is what you're going to be doing in terms of answering questions or just kind of going over galvanic and voltaic cells. Make sure you know what happens in this whole situation: who loses electron, who gains electron, what are the end results, what's the purpose of Salzbridge and all that. Be able to calculate the E0 of the cell eventually, and then be able to calculate E of the cell under non-standard conditions, including the delta G standards and the delta G non-standard. One thing I do want to leave you off here, if you have, let's say, um, we already talked about something being non-spontaneous. So non-spontaneous, you have delta G to be positive number and E of the cell to be in a negative number. And then if it's a spontaneous, and I can certainly say for both of them, delta G standard would be in a positive here, and E0 standard would be in a negative here. If it's a spontaneous, the delta G standard and delta G non-standard, they both needs to be negative to consider that spontaneous. And then E0 of the cell and E of the cell both needs to be positive to consider that spontaneous. But what happens if your battery or if your reaction hypothetically is at equilibrium? So at equilibrium, you would still have some value for the delta G standard. We don't know whether it's going to be positive or negative. That really depends on whether the equilibrium is product favored or reactant favored. That's a different story. It would have some value. And same story, I could very well have some value for the standard E0 of the cell. Again, I don't know whether it's going to be positive or negative. That really depends on whether the equilibrium is product favored or reactant favored. But one thing you do want to keep in mind that the delta G under non-standard conditions at equilibrium would be 0, and the E of the cell under non-standard condition would also be 0. That's a very important thing at equilibrium. And this is when you start relating multiple, like I can relate delta G standard, E0 of the standard of the cell, and K equilibrium constant. So remember, let's say delta G standard here, E0 of the standard, and K equilibrium. I don't want to talk about delta G non-standard because at equilibrium, it would be 0. So you want to make sure you can go back and forth on this between those two relations, go back and forth on those two relations, and you know the equations for those two relations as well. We already know for the E0 for the cell, so delta G standard is going to be equal to negative NF E0 of the cell, and then the delta G and KEQ is going to be delta G standard equals to negative RT natural log of KEQ. And the E0 of the cell and the KEQ relation actually comes from the Nernst equation that we got up here. You just go and plug this in 0 and then see what you get out of it. So that would be E0 of the cell equals to 0.0592 over N log of KEQ. So sometimes these three equations are going to be helpful depending on, what are you really given and what are you really trying to find out in that particular case.